Everyone can hear me okay?
A lot of Apple policy.
So again, I'd like to echo Bob's comments, but just thank you very much for putting this on to the Watershed Council. This is such an important discussion, and we're certainly happy to be part of it, and doing our part to hopefully provide a bit of information and provide some answers for you as well on some of the concerns. So my job here for the next 15 minutes is really to give you a bit of an overview on the prevention of leaks. It's about pipeline integrity. It's about keeping the oil inside the pipes. That's what I'm here to talk to you about. There's a massive science behind this. I'm going to try to keep this at a fairly high level, brief level. I'm going to talk about some of the tools and criteria we're going to use. Harold's going to get a bit more into the criteria than I will after me, and then certainly I hope everyone will raise all your questions in the question period. So in terms of guiding principles, our goal is 0 leaks. It is pretty blunt as that. We maintain our system as a long life asset. We don't put a life on the pipelines. They should be able to go indefinitely. What we do is we monitor them all the time, and we repair as needed. And at some point, we determine end of life, basically because the cost of repairing is too much, and it's easier to replace than repair. But effectively, there is no end of life. And then we want to work with all the different stakeholders, regulators, public, industry partners, everyone else, to make sure we can optimize our programs and do what makes sense.
I don't know.
So our approach, again, when I talk about tools, I'm talking about a very holistic approach. So pipeline integrity doesn't start once we start shipping oil. Pipeline integrity starts very much before that, during the design, during the concept selection. There's lots of stuff we do right at that point to make sure we're designing a safe pipeline. During construction, there's many different things we do to make sure that the pipeline will be constructed and be able to be maintained safely. All through operations, there's, again, many different things we do, and certainly into decommissioning as well. So that's one thing I want to leave with you, is that it's not just during operation. It's well before that and well after that. Another concept I want to leave with you, and people who are in the chemical industry will probably be quite familiar with this, but it's the concept of a multi-layer defense. We don't rely on any one thing to keep us safe. We try to have many different layers of defense. And it's a kind of well-known model, James Reasoner's Swiss cheese model. If you only rely on one layer, no layer is perfect, so something might slip through. But the more layers you can add onto it, the more chance there is some of these layers are going to catch whatever problem is coming up. So one theme I think you'll see through this is that there's many different layers of defense that we utilize to keep our pipeline safe. And in very general terms, I think we talk about preventing any threats. We want to monitor the condition of our pipelines, and then we respond and we mitigate anything that goes wrong. So in terms of prevention, on the left-hand side, there's 4 basic threats that we're trying to measure for, monitor, and then there's a bunch of prevention measures. And even within these measures, there's many different tools. So if I were to give you a list of all the tools, there's maybe 50 or 70 tools or something that we use, and it's all through a whole suite of different things. But at the basic level, integrity threats, if there's a leak, it's happening for typically 1 of 4 threats. It's metal loss, which is typically corrosion. There's some cracking, deformation, which is typically third-party damage, something hits our pipe. Or there's in our facilities, we have lots of different equipment like seal leaks and stuff like this that we're trying to monitor. And in terms of diagnosing, we use a full suite of tools. Some of them are very scientific, very detailed, like the inline inspection tools, and I'll go into a few examples of that as we go through this. Some of them are as simple as doing visual inspections of different pumps and pieces of equipment. There's online sensors which measure strain, stress. We do cathodic protection. Hydro testing is appropriate in some situations, but in others, non-destructive examination. There's just a whole suite of tools that we use. Particular to the straits and getting water body, There's lots of surveys that we do. We use remote underwater vehicles to take pictures. There's GPS. There's ultrasonic testing. It's fairly all-encompassing. In terms of some of the technological tools, this is a generic sort of picture, which is what we call a smart pig. Basically, a lot of computer stuff built into a pig that goes inside the line. The oil pushes it along. We measure a bunch of stuff, and I'll go into the details here a little more. And it comes out, and we analyze the data at the end. Typically, these things are fairly standard. There's always some drive cups which allow the oil or the fluid to push it along. There's always batteries. There's always some electronics and some computer memory cards, and then there's the actual instrumentation. And there's a bunch of different varieties of instrumentation we can do, and they all have some strengths and some weaknesses. So again, we use multiple versions of these tools that provide that overlap of systems to keep us safe. This is sort of state-of-the-art science. This is the best technology that's out in the world. And this is the same stuff that's used in hospitals. So we talk about UT tools. UT is ultrasonic testing. Well, UT is the same as an ultrasound in a hospital when you're getting examined, whether you're pregnant or whether you've got some sort of condition that needs an ultrasound. We talk about magnetic flux, MFL tools, magnetic flux leakage tools. That's the same as an MRI tool in a hospital. We're using the same technology. We talk about non-destructive testing. Often that's X-ray. Again, same thing as a hospital. We're looking at the pipeline on a millimeter by millimeter basis. We're looking for any little thing that's out there. And so you can imagine, we've got about 16,000 miles of pipeline, and we're looking at every millimeter. We're finding lots of stuff. There's a tremendous amount of data. And we analyze all that data, and we use algorithms and computers, and we use, probably thousands of people that are analyzing this stuff all year long. And we're looking for those small little defects that might only be 2 millimeters wide and long and deep. And we need to understand what those look like and if they pose a threat to our pipeline or not. So the next about 4 slides or so is a few details on some of the tools. I won't go into them too much, but I've got some pictures and I've got one sample of some of the output that we see. And like I said, we use multiple varieties of technology. There's MFL, there's UT. They're all good at certain things, and then they all have certain inherent weaknesses. So that's why we use all these different tools, so we can get a full picture. In particular, this is about corrosion. Corrosion tools have been around for a long, long time. We understand them very, very well. We understand where they perform very, very well. Lots of good experience. This is some typical output from corrosion. So this bottom chart here is one version of output, and what we're looking at here is just this gray box is just the part of the pipe that's being analyzed. These red dots just indicate there's a bit more metal loss. And when we're doing the analysis, those are the things that get flagged to us, and we look into them in a little more detail. This picture here on the right is just another sort of graphical depiction of that. Again, it depicts on how much metal loss is there and where do you have to look and how detailed you go. When we get to the point where we actually make the call that we have to go look at something, this is the actual piece of pipe. So we went out there, we excavated it, we identified a flaw, and we wanted to understand more about it, so we cleaned it up. This part here is the actual corrosion. You can see, I'm not sure how good you can see from the back, but we do the non-destructive testing. We measure how deep it is, how wide it is, how long it is. We do the calculations to say, is this a problem for us or not? What do we have to do? And then we do whatever repair we need to do to make it safe. Often that involves putting a whole new metal sleeve around the pipe to keep it safe. But anything that is a remote concern to us, we'll dig up and we'll analyze physically, and we'll figure out what we need to do to keep it safe. This is the cracking tool. Again, uses the same sort of technology in a different tool. Ultrasonic testing, MFL tools, magnetic flux tools. This is one where it's got both built in. It's by GE. We have a number of different companies that we use to manufacture these tools and run these tools for us and do the data analysis. GE is one of them. This is a deformation and strain tool. This is a geopig. It uses GPS in there, so we track exactly where the pig is at any one time. We can use that to locate whatever it finds. This tool is really used for identifying things like these gouges or dents or buckles. Again, samples of output which characterize any areas of concern, which we'll go and we'll analyze. Gyroscopes are in here, GPS, ultrasonics. Again, lots of science goes into these things. And the last tool I want to talk about is a relatively new one, and this is really one of the learnings. That someone asked the question out there about what have you learned from Marshall. This is one of the things we've learned. And again, I go back to that whole concept of defense in layers. This is a secondary analysis that we do that is a new layer of defense that we put on it. So we've done, since Marshall, we have spent roughly $4 billion, probably more than $4 billion, just on integrity. That represents a massive increase in integrity spend. And as part of that, we've analyzed tens of thousands of locations. And when we analyze it, what we end up doing is we do these scientific runs, we run the ILI tools down, they tell us something, and they give us let's say they give us an indication somewhere, and we go out and we dig that indication. And we compare the indication, the real found data in the hole, compared to the ILI data. And what we want to see is we want to see a high correlation. We want to see them matching up. What that tells us is that our tools are really good at finding exactly what's out there. That's what this chart is showing here. This chart measures, this is called a unity plot, and it's pretty common in integrity discussions. On the bottom axis here, this is what the ILI tool called us. This is what the ILI tool identified as the defect. What this vertical axis is what we actually found in the field. So this line that's going on a diagonal is called the unity line. What we want is everything bang on that line. That would be ideal. It doesn't always happen as ideal in the real world. So we want everything as close as we can to this unity line as possible. And when we've got this much data, if we've got 10,000 parts or pieces of data or more, we can start doing some advanced analytics on it. And it's really about statistical modeling. And we can say, you know, if everything correlates really, really well, we're really confident in that tool. If things don't correlate really well, we know we have to do more work. And some of the things we do in terms of more work, if we aren't real confident in our tools, we'll do things like hydro test. And we're testing right now line 2. And that's really because we weren't getting the clarity on the tools that we wanted to see. So we said, forget it, we can't rely on them 100%, we're going to go test this line. And so this is really a brand new thing. Enbridge is one of the only companies doing this. There's no codes and regulations that say you have to do this. But this is an added layer of defense that we're doing to make sure our lines can be kept safe. In terms of criteria, there's a bunch of codes and standards that set out the minimum criteria that define when we need to dig and what we need to identify as a flaw. And they're set out by CFR. In Canada, it's CSA Z662. API's got a bunch of recommended practices that get referenced in code, and we also follow. But we don't just go for minimum. We will analyze all those things, and we'll certainly meet the minimum. But in certain cases, we want to go beyond that as well. So we've got our own standards that we want to adhere to as well. So really, in terms of summary, we are committed to zero leaks, and I think when I say committed, I don't use that word lightly. You know, we spent $4 billion. We've increased our team from probably about 30 people to 180 people in pipeline integrity since Marshall. We have got new VPs, new directors for integrity. It's been a massive commitment over the last 4 years, and we are committed to keeping the pipeline safe. Again, we look at this from a long life critical infrastructure asset approach. We want to keep every pipeline equally safe. Some require a bit more work than others to keep safe. Some just were inherently designed, or not designed, but the construction and manufacturing processes were better in the day. So they're easier to maintain. Some take more resources to maintain. That's life. We want to keep them all safe. And I'm at the end of my time, but again, I just want to emphasize that we appreciate forums like this because we want to work together and collaborate with everyone, whether it's PHMSA, whether it's Coast Guard, whether it's EPA, whether it's the NGOs, the rest of industry. We're all in this together. Thank you very much.
Thank you, David.